Hello and welcome back to the channel. It's Mark from PowerSonic and Apprentice 121. We are on another solar job with a twist. This one's going to include an EV charge point. We have got some outdoor consumer units, lots of submains and considerations around selectivity, and the usual interesting aspect of how we're going to fix this stuff onto the roof behind me. This is for a friend of the Apprentice 121 family. Hopefully we're going to get to speak with them as well through the course of this video. We'll see if they're up for that. Without further waffling at the beginning, let's take a look around and see exactly what we've got in store on this one. So as is best with these things, start at the beginning. This is our main intake. So we've got a 100 amp head. We're going to be putting solar and EV on here. We've got an existing set of tails running through to the customer's property, but there's changes at large with that. So we've got things to consider there. We're going to drop a little enclosure in under here and house our switch fuse to take power to the new location where I'll take you in a minute. It's quite a distance away. And then we can put the protective devices we need for that in here. You'll note this is just line and neutral. In here it is a TT supply. So we've got an earth rod down here on this building and there's various earth rods throughout. This is quite a large site with different buildings and different things to consider along the way. And we'll be doing all of that as we move along. Matthew is currently working in the carport over there where the EV charge point is going to live. So we'll show you all of that too. And inside here is where the solar equipment is going to live. So this is a workshop that is going to be converted. It's all going to be boarded, insulated and changed to habitable space. The customer's got some big plans with all of that. But for the minute, our 25mm supply cable comes in. The guys have landed it in the board already and we're running up and away into our main switch. We'll go in a bit closer and have a look at that in a minute because there is some interesting design considerations that we've taken with that. You can see we've got our solar link, if you like. So this is what we would usually put in place between A and B on these two particular bits of equipment. And then obviously our strings running away. And you can see they've got that ready there for the array that's going on this roof. Sorry, it's going on this roof. And then we pass through into the other side of the workshop here where we've got another array going on the other roof. But we'll deal with all of that probably in a later video. So looking at this here, the customer. So this is Matt, who's been helping us out with some stuff. It's his home. He's also a friend of Apprentice 121, runs the Facebook community. We'll have a little chat with him in a bit, but he's popped us this backing board up. It is absolutely rock solid. So we've got some studs on there. Again, it's really uneven wall surfaces, as you'll see here. So we couldn't realistically mount this concrete sheeting straight onto it. It's battened and boarded behind, and then the fireproof board on top. We've got our trunking, as we always do, running top to bottom. And then we've got our DC isolators and our AC isolator. And this system is going to be the new GivEnergy All-in-One. We're going to do a special one-off video on that. So mounting all of the Give stuff will be in a future video. But essentially you have the GivEnergy AC coupled battery system with the gateway and an inverter. So we're going to have a whole array of equipment on this board. There's plenty of space for it. And then the isolation points that we need as discussed on prior videos. And then we've got this cable route across here which carries the the AC feed across to the consumer unit and our DC strings up into the outlets here, and also a CAT cable. Important to note that these are all reinforced double insulated cables. They're all rated to a minimum voltage of 300 and that minimum's on the data cable. The AC and DC cables are rated to 600 volts. So we're more than okay with that. Now this consumer unit, we have here, as we know, the TT, and we're going to have an SPD in this board because we're a distance away from our isolation point at the meter cabinet as we've shown, and these are type 1 and 2, so these are used primarily for TT overhead supplies, which is what we've got here. So we've factored that in. We've also got a main switch down here for this board, as you can see, so that's going to isolate everything in here. And you'll note over there we've got a fuse, so this is going to be a 60 amp fuse that feeds down our 16mm steel wire armor here and runs across to the carport where we're going to have another sub board over there, and that's really for selectivity. So we'll cover that more as the video progresses, but just to put that out there at the start, that's what we're looking for. And this board is largely going to be empty, otherwise we're going to have our circuit leading over to the carport, and we're also going to have our circuit for the solar. The rest is just going to be blanks because, as I said, this is all getting converted and the customer's going to be running new circuits into here through the course of that process. But for the time being, it's pretty sparsely populated, isn't it? Lots of room, we like that. If we wander across back to the carport, I can show you the distance there. So this 16mm cable is in an underground duct. For those of you who've watched the Apprentice 1-to-1 channel, you will have seen we've done a little design series on there where we considered routing cables underground and some of the derating factors that are involved with that. Not all of them, just some of them. And you can see over here, originally the customer had a BG setup. So this is one of their outdoor consumer units, supposedly. There's a bit of question marks over the IP ratings and usage of those, but we'll not get to that just now. And they were using a granny charger BG effort here, so you can see these are the suitable for electric vehicle charge point outlets, and David Savory's put a review out recently on those. And up here we've got our subboard, and this is contained in an IP66 enclosure. So this one's from MCG, and it's GRP, so that's glass fibre reinforced, or whatever the letters stand for. And you can see we've landed through into the bottom to maintain our IP rating. Bit of a fiddle with that, because we wanted to try and limit single insulated conductors inside the actual enclosure itself. So we've taken it through and then landed into the board, which made it a bit of a faff, but Matty's done a sterling job getting that in there, in fairness. And we'll be doing the same when we land our final circuits in here. So there is going to be a car charger over there, a proper one. So we're going to have a Zappi. We've taken our 6mm feed across for that, and you can see that runs across. That's going to land into here in a similar fashion. And equally, we're getting rid of all of this, connecting in some new lights, and the customer's got a socket over that side that they want to keep. So we'll be repurposing that, but largely that's all coming out. You can see in here there are a couple of unique features. I'll zoom you in a bit closer and we can talk about them. So there's a temperature controller there. These are from Schneider Electric. So that one, having the red dial, is for heat. So this is going to essentially turn on at a set temperature to activate this heater in the GRP enclosure. And that's to try and limit our minimum temperatures in here, because these protective devices start to behave differently when those ambient temperatures adjust. We're not too concerned about them in the summer, because having done the derating calculation, it plays out fine. But in winter, we don't really want them dropping below 0 degrees, because they start to operate at a higher current and the time curves adjust. And we want to be really careful, with this being a TT install in particular, that we're limiting those ambient adjustments as much as possible. So this is a 20-watt heating element. You can see it's got grills on the bottom and the top. And when the temperature gets to 0 degrees, we're going to set this quite low. It won't be 0 very often, but when it is, it's going to use that 20 watts of energy to just warm this space and allow for those protective devices to have some element of control on the ambient temperature. And again, our MCBs and RCBOs, so 61009, 60898, are pollution factor 2. So we need this inside another enclosure to take it out of that. Essentially, the pollution factor rating would apply to the enclosure as a whole, which is then inside this IP66 MCG enclosure, which is suitable for use in pollution factor free environments. So we're offering protection for them in terms of the ambient temperatures and as an enclosure around them as a whole. And I think that gives us a happy medium in terms of using MCBs and RCBOs in outdoor environments. Now, the other factor that we've done with all of this, these are actually graded as 60898s and 60947-2s. So these are dual product standards from Proteus, which is useful because the 60947-2s have much less movement intolerance due to temperature and other such factors, and they're typically used in commercial environments. So they're commercial grade equipment, which is useful to know. Our earth rod on this one, you'll see, is down in this corner. We need to have a bit of a clear out to get to it, but we've got an existing earth rod down there, and that runs up, and we're going to take that across into our new board. Obviously all of this is coming out, as I said. So we'll have this on a TT, and then our final circuit out is on an RCBO. And again, we'll talk about the selectivity of the RCD element on this as well, because that's also important. Looking out to the wider install, again, you can see we've got these two roofs. So we'll speak about the solar now. There's some Veluxes in this roof over here. We're going to try and fit a couple of landscape rows between those. So hopefully we can get 4 panels on that roof. And then over on this roof here, we've got a much larger space. It is deceptive, but again, 2 rows in landscape across there. We've actually got some shading from these trees, so we're using optomisers on all of these, and again, that'll probably be in a separate video. These are a new tile on us, so these are like a flat tile, So it'll be a different type of hook flashing kit and one of the spongy little tiles you put underneath the hooks to stop all these cracking. But again, we'll cover that in a future video. And this is going to be the board that's going in our enclosure near the meter cabinet, as I showed you at the beginning. So we've got our fuse that goes into here, and we've got 100 milliamp time delayed, sorry, 300 milliamp time delayed RCBO going at the start. Again, with this being a TT install, we need to have that RCD protection on our cabling for both fault and additional protection. So there's no real way around it. And we've got our fuse in here. This, again, is going to be the only area where we might have some selectivity issues because it's going to be rated the same as what's in the meter, main service fuse. We need the capacity really, so it's one of those things where you would obviously hope to put an 80 amp to have some element of selectivity, but truth be told, if there's a short circuit major issue, the chances of either one going before the other, if you look at the selectivity chart, you know, it's a best guess scenario. So it's not really changing anything, and having the fault and additional protection through the time delayed RCBO should hopefully prevent that from ever being a scenario that could occur. But that's the one little area that we've not been able to achieve. So obviously having this 300 milliamp time delayed RCBO at the start, that would cover our cable coming down to here, which then runs into this main switch, and then obviously the final circuits here are going to be RCBO 30 milliamp. So we've got the selectivity between that main fuse, thinking of it for the MCB side of the RCBO's operation, and the operation of that. So on a direct short circuit, these are going to operate much faster than that 100 amp fuse at the origin, and equally in terms of the RCD, so in an earth fault, these RCBOs would operate more quickly than the time delayed up front, so it's not going to take the whole install out when one goes. What you don't want is an entire install hanging on a 30 milliamp RCD at the beginning, because obviously one earth fault and there's every probability you're going to take that out. Even if you was to use 100 milliamp in this case, you know, you may be pushing onto the realms of, you know, what's acceptable. And the reason we've gone for 300 milliamp time delayed up front with this bin TT is the inverter says if we are going to use RCD protection, to ensure that it's a 300 milliamp variety. I believe, I need to check that, but it gives us the protection we need anyway. And then here we've got our fuse that we're using again to run over to the carport, and this is going to be 60 amps. And the reason we've not used an MCB on that is because we're going to have MCBs obviously in the RCBO element at the carport over there, and we didn't want the issue of this going pop with that and taking out the whole supply to the carport. Not that it's a huge issue in truth, it is still bad design, but it wouldn't be a huge problem, flashing LED lights, if the whole supply to that carport was lost from here. But there's ways to design around it by using a fuse. So if we're using a 60 amp fuse here, we have skipped a fuse version out between our main intake one, again at 100 amps to 60, and then running over to the carport, we've got final circuits where we're going to have a 32 or 40 on the car charging point, and then a 20 amp and 6 amp for lighting and such. So the next drop down is to 32. So we've skipped out between 60, quite a few values on the fuse, and swapped to the MCB, which should go much quicker than this fuse would. However, if this was a 50 amp RCBO, because that's the maximum size up you can get in that configuration, you would potentially be taking that out on short circuit alongside possibly those ones over there. And again with the RCBOs in that board, so they've got local RCBO 30 milliamp protection, and then this steel wire armor cable running over from that again, its RCD protection is coming, if we go right back to the start, out of this time delayed variant as well. So our steel wire armors are covered with that, leading out to all of our sub boards. So that's how we've set it up to try and give us some selectivity. Again, if we'd popped a 30 milliamp RCBO in here, it's not the end of the world. Again, if we get an earth fault down at the carport that turned the whole lot off, however, it's avoidable. So that's the reason we've gone for that. I hope that makes sense. So having had a chance to look around the install, I thought I would very briefly interrupt the video here and credit Jamie Blatant from over on Instagram. For those of you who've been following along on social media through the course of this week, Jamie, in his own brilliant and unique way, has been expressing his thoughts and views around outdoor consumer units, and it tied in quite nicely with some work that we had going on this week. So he has inspired the content here for me to put forward our approach in terms of using some of this stuff in what might be termed an outdoor environment. And I'm not doing this as a way to lecture and show we're better than anybody else who approaches these things in different ways. I'm discussing the core issue underneath all of this. So I want to focus in on that. But Jamie's raised another interesting angle on this that's got me thinking again, and that's to do with RCD protection on metal equipment that's outdoors. Now, those of you who followed the news a year or so ago, it's perhaps longer now, where unfortunately a young lad lost his life due to electrocution in a pub garden space. And ultimately that was down to a lack of RCD protection and earthing on some external lighting. And one of the issues I'm potentially concerned about that are perhaps outside the realms of the regulations, because the way this stuff's been installed, from what I can see, doesn't breach that. But there is issues there. I think he's raised an important angle of discussion, because typically one of these outdoor consumer units that are perhaps made of cast aluminium could be mounted down the side of someone's house adjacent to a meter box, and you could have kids booling up and down there with their bikes. And essentially that 100 amp enclosure has no RCD protection sat leading up to it. So it's another interesting area for discussion, and again, credit to Jamie for raising that angle on it, and go off and check his content out over on Instagram if you want to see some more of his opinions in and around all of that.
So I thought we'd take a minute to have a look through the electrical design, and on this one again I've used Modexsoft Electrical OM. If we have a scoot up to the top of this, you will see our supply coming into the property has been set and defined. So if we pop into here, we can see we've got a TT supply. And if we go along to our earthing, we've set the earth electrode resistance and all the other things you need to do that I've shared in videos before. So we'll zoom in a little bit at the schematic first. You can see we go through our main service fuse, through the electricity meter. We have some tails, which then run into our service fuse, if you like, within the switch fuse with the time delayed RCD, as shown in the video. We've then got our circuit leading out to the workshop, and that's 28 meters long. So we've got some considerations around volt drop and our protection of circuits. So we'll speak about that a little bit later on. We've got our SPD, and that's all been defined as the switch fuse at the beginning. We then loop down into this workshop distribution board, and there's lots of final circuits that I've popped onto there. So I just need to adjust these so we can see them in the layout a little bit better. So all this is adjustable from Electrical OM when you're messing about with your designs. So as the schematics laid out, if you're not happy with how it's displaying, you can just move it and tweak it so it all comes together in a sensible fashion. So I've not finished with this one yet. There is some sweet tweaks still to be made. But you can see over here on this side, we've got our SPD. We've then got our solar PV circuit. And the beauty of Electrical OM again is that it will now show the DC strings. So we've got cable calculations on these as well. I still need to add in the DC SPDs and such, and again make some changes so you can see the isolator is shown there and it doesn't actually exist. So if we go in there, we can take it off, go back to the schematic, and that should now be gone. So that's the beauty of looking at what you're doing. You can see exactly what's going on. And we'll have a little look through the actual circuit arrangements in a minute. And then you've got all your usual sockets, lights, cookers, immersion heaters for the eddy, an air source heat pump, and then jumping out over to the carport board that we showed you there. So if we have a look at the carport, you can see in there we've got our heater circuit, we've got some power and lighting, and then we've got the EVSE charge point. Now, obviously, as all these circuits build out, you can see there's quite a large install there. Volt drop is the enemy with this. So if we go and have a look at one of the final circuits, if we open up the lighting, for example, on this circuit here. So this is the carport lighting. And if we have a look at our volt drop, we've got 2.34% as a maximum. Now, obviously, we've only got 3% as a maximum allowable on volt drop, so we're within that. But as you adjust your loads on some of the circuits leading out of the boards preceding that, you can adjust the volt drop that's going to occur at the end of that line. So you've got to factor it in with your design stage and make sure you are covering that off. For example, this workshop board, If we're looking at the length of the cable here, it's 28 meters. If we was to increase that, say, to 50 meters and see how that starts to play out, I'd expect to see a few warnings. So you can see we've got warnings pop up on our design. If we go and have a look again at that carport lighting, we can see our volt drops now moved to 38%. So length of cables and loads you're expecting in your design are going to massively affect how these things play out in the real world, and it's fantastic to be able to run that through this software and sense check yourself. So as we've seen in the course of this video, we've got issues around environmental conditions, we've got issues of selectivity between our protective devices, both for fault conditions and with the RCDs, so the MCB aspect of a RCBO and also the RCD selectivity as well, and then volt drop. So we really do have to be very careful with our design. And you can see here we're just about ticking all of the boxes. There is one issue of selectivity, and I spoke about that in the video. So if we go and have a look at in the protective devices area of this software, you see the selectivity study. It's highlighting we've got an issue. So if we have a look at selectivity, you can see here we've got the graph which shows these items in their time curves. So we've got our main service fuse and the fuse we've got in our switch fuse, and they're on exactly the same time curve because they're exactly the same thing. And we've then got our upfront time delayed RCD, which has got its own selectivity graph as well. Now you can see we've only really got one alert of selectivity shown in this, and that's between these two fuses at the start. So if we go to something at the end of line, so again to the carport, and we'll choose the EVSE, you can see you get a lot more data on there. So we've got these generic fuses that are all playing a part in that circuit. We've got our time delayed RCD. We've then got the generic fuses in the workshop board. So that's our 60 amp fuse that leads off to the carport. And then we've got the final circuit down in the carport for the EVSE. So that's our 30 milliamp A-type RCD with 40 amp MCB built into it effectively. And also we've got the selectivity achieved between the fuses leading up to it and also between the RCD preceding it as well. So we've achieved some elements of selectivity within our design. How this plays out in the real world, it does vary based on other factors out in the installation day to day, but that gives us a strong start point to hopefully achieve operation of the right device when you get a fault in the circuit. So if we were to go back and look at our switch fuse and change the value of it to 80 amps, because then we've got an element of selectivity between that main service fuse and other aspects of the design, you can see now it's cleared the fault of selectivity, if we're going to call it a fault on that. And if we go back and look at the selectivity study, if I save those changes, you'll see now we've got separation on those two places. However, we've got a red warning come up now on the carport, and that's our 60 amp fuse here, and you can see we've got an overlap between the 80 and the 60. So we've solved selectivity in one place and introduced an issue with it in another. And again, under short circuit conditions, from the experiments we've conducted in the real world, it is very much a case of all bets are off when you've got a dead short and there's enough current flowing. So it's one of those, you're never going to get full selectivity in most domestic environments when you're working from a 100 amp service fuse and you're trying to put in lots of submains. It's just not a realistic prospect. All you can do is try and get some partial selectivity and give yourself a fighting chance, which is what we've got here. So if I go back into the switch fuse again, and we'll just pop that back to 100 amps, so we are back where we started, apply those changes, and you'll note the carport issue has cleared itself up. So as a final thing to do with this software, once you've made your design, is you can generate your report. It's telling us about the selectivity warnings, but it is going to produce us a report. I've ticked every single box in here, so the level of data that this spits out is off the scale, but it gives you that full confidence in what you're proposing to a client has been correct. And that includes aspects of your AC design and also your DC. So you can see it's laying out all of your circuit arrangements with your cable types, any power factor and correction factors that have been used. Everything is in there. This is such a long report. I'm just going to sit and scroll through it really fast. If you want to try the trial on this, you can use it free for 14 days. So you can go off and play with it. It really is quite straightforward to get used to once you have got your mind around it. So it's well worth putting the time and effort in, and it does help you massively with your design. You can also do arc flash studies as well. I've shown that on my channel before. So if you're working around main panel boards, for example, and you want to know of the type of incident energy that might be there, it's baked into this software. So as I say, the detail in here, just scrolling through, you can see it's absolutely off the scale. So if you've got any doubts about a design process, none of us know everything about all of the books all at once. Having this to sense check yourself is an absolute game changer. And just to quickly show you inside one of the circuit designs here. So this is a socket radial circuit. We've got about 2 kilowatts of load into it. We're using our flat twin and CPC, so all the cable types are in here to just pre-select. You set your length and you set your CSA. So in this case, we've got a 4mm. Your protective devices again, you can change all those. It's got the manufacturers all in here listed, so you can choose whichever breakers you're using. And then obviously with this being a TT, we need the 2-pole RCD protection that we've got at the switch fuse, but it's also very helpful at your 30 milliamp level to have that baked in as well, and thankfully the Proteus RCBOs as shown in this video achieve that. So just to quickly show you it shows you the current you're using, if there's an AFDD involved, as you can see here, the maximum touch voltage you want to achieve, the volt drop that you've got going on in this circuit. Again, we have a little bit more generous allowance on a socket circuit, but all of that is in there for you to view. And then you've got the overarching schematic, and again, this is all outputted in the report, and it'll actually produce you a line diagram as well. So say we were to go into UK Forms now, and we wanted to create a new certificate to, pass on to the customer when they're signing all of this off. If you go into there now, we should be able to view the distribution boards, and they should all be pre-populated with what's actually going on in them for us to enter the test results. So it saves a lot of time at that level as well. Let's move on with the video.
So that's the board about ready now as far as we can take it. Got the steel wire armour cleated up. Just a stuffing gland in the bottom to try and stop any moisture and insect ingress into this enclosure. We've got a flexible cable that's heat shrinked over on these connections. You can see that in there. See if I can put the torch on. There we go, and you can see in there we've got the heat shrink over the inner conductors and also some heat shrink pushed over the outer heat shrink, if you like. So we're trying to maintain an element of protection to that cable inside this enclosure, and we're going to put some perspex over there as well, just to try and stop any access to live parts for someone who's opened this enclosure. Obviously we're going to have warning labels on here that there is live voltage within. There's a point of isolation ahead of this board as well, so there shouldn't really be a prospect of somebody interfering inside here, coming into contact with live parts. But it helps to try and ensure you've got a level of protection for inside an enclosure such as this. And then we've got our consumer unit in here with some thermal controls to try and offset, as discussed earlier. We've got our final circuit running out. Matthew's just going to tidy all this up. He's busy on with that now. So we've got a little junction box up here which runs off to a socket. This little junction box is just for these existing lights at the moment, so they can be put to use. This old BG board is now in the scrap pile waiting to be recycled. And I think that's about the best that we can do in the environment this has been installed into, to give us some control and make sure we do have overcurrent protection when we most need it. We've got our type 1, type 2 SPD that we need, and we have got our main switch which kills the power off to this board, and then we've got a final circuit running over to the carport which is a fuse. Important considerations around selectivity and also all of the pollution factors. At the minute this is a workshop environment. It is going to be converted into habitable space. The customer's going through a massive process of renovation. For the minute we're happy with that as is. We're outside of the weather and we're inside this space where we can keep these at a relatively straightforward ambient temperature, and considering the derating factors based on our overcurrent protective devices and the cabling selected, we do not have an issue. Happy with that. So you will see down at the carport we have this IP66 enclosure from MCG. We've got this Proteus consumer unit within, and there are some new products and devices that you might not have seen on our channel before. We'll speak about that in a minute. This has our 16mm submain come down. Again, we're on a TT. Earth electrode is over there under all of the scrap metal, and we need to have considerations around selectivity first up. So this 16mm is protected by that 60 amp fuse in the workshop consumer unit, which is protected by the 100 amp fuse at the meter cabinet. And we've also got the time delayed 300 milliamp RCD looking after this supply cable to this point. We've then got our 30 milliamp RCBAs, so we've got selectivity with the fuses and the RCDs covered. However, at this location, we are going to have an EV charge point. Now that EV charge point is going to be running at 7 kilowatts for prolonged periods, and we want to ensure our overcurrent protective devices are reliable, so we're not exposing them to wide variation in environmental conditions because they wear out faster, and they also require derating due to that. So when we've got our RCBO here, which is going to be of B40 variety to cover off the summer temperatures, because we're not worried about the upper limit, for example, that's why we've gone up to a B40. That might start to behave at 35 amps when the temperature reaches 40 degrees C, for example. But we are a bit worried about winter when that B40 might start to behave like a C50, for want of a better example. And for us, that's not acceptable. So we're adjusting our design to incorporate this enclosure and this heat controller. So this is from Schneider. They come with blue and red dials. The blue dials are typically used to activate fans to cool enclosures down in summer. The red dials are to activate heaters to help with ambient temperatures and condensation in winter. Very common in large-scale EVSE, which is all outdoors in the green GRP enclosures. So this is GRP, glass reinforced fibre, whatever it is. And that is a similar principle we're applying to this here. So when that temperature reaches 5 degrees, which is what we're going to set it to, it will activate this little heating element, which will just warm this enclosure to try and eliminate condensation and also stop the overcurrent protected devices being exposed to the harshest weather temperatures in winter. The customer already has one of these IP66, IP65 enclosures from BG. You can see that's largely exposed to the elements, and my understanding is they're pollution factor 2. This environment for me is pollution factor 3, pollution rating 3, whatever you're going to call it. So it's not really suitable for the use in that space. Equally, this consumer unit wouldn't be unless we popped it in an enclosure that is. So this is our IP66 GRP enclosure with a bit of heating to stop it getting too cold in winter. We'll have a condensation release valve as well in the bottom. And I think that gives us the best prospect in terms of reliability and also safe operation in the worst circumstances. Speak about that in a minute. Okay, so a final point of note around derating of overcurrent protected devices when they're used in unheated spaces and the considerations for it. There are a few key angles that need to be covered off due to that. One is the pollution rating of the products, very common in commercial and industrial environments. It's always a design consideration. And the other is the derating due to temperature. Now, typically when you're using, for example, 20 amp radial socket circuits or lighting circuits that you know are going to be lightly loaded, it's unlikely to be a problem. MCBs, RCBOs have an operated rating from -30 to +60 for their applications of use. You just need to make sure you derate them based on it. Where it gets a little grey and sketchy is when your earthing systems change, and also when you are using higher load equipment. So EVSEs, for example, EV charge points. If you're going to pop them onto a 32 amp RCBO, chances are it's going to operate in sunshine. The worst colour for an outdoor consumer unit is black because it absorbs all that solar energy. That's why solar panels are generally coloured black, so they're going to get a lot warmer. Those ambient temperatures will be higher in direct sunlight, so you need to factor that in. And then again in winter, if they've been exposed to -5, -10, it's not unrealistic to see that on certain days of the year. You need to factor in the derating value from the manufacturer, ask them for that to understand how that breaker will operate on that particular day of the year when someone stood there using the equipment connected into that circuit. It's all well and good saying that most of the time it's 20 degrees and it's all going to be fine and rosy, and it will be. That 99% of the time will be the case, but the 1% of the time when we really need to rely on our overcurrent protected devices or smoke alarms or whatever else is when you really need them. And that could be on a day that's -10, it could be on a day that's +40. Don't discount it from your design just because it doesn't happen very often. It really is that important. So the final point is to do with longevity. So your normal 60898s and 61009 RCBOs, MCBs are designed for using in household environments where they're very reliable and will last a long, long time. Now, obviously, if they're in environments at pollution category 3, they're exposed to wider environmental conditions where that duration will drop. Obviously, again, if the circuit's regularly loaded at 7 kilowatts, it's going to be exposed to more extreme use than a lighting circuit, for example, and naturally you would think it would wear out faster. So you may be getting warranty callbacks to go and swap this. You need to understand how long the manufacturer warranty is and your own labour warranty and the resulting callbacks that may result. So that's outside of the safety aspect. So I would generally try and avoid using things outside in a pollution category 3 area unless they are correctly rated for it. That's my personal view. I've tried to set out the safety reason and also a business case for not doing so. I do understand where decorated homes and difficult cable routes will lead you towards using an external consumer unit. If you factored in derating, if you're happy with the safety aspect and you're happy in terms of the potential for failed products, then that's fine. You carry on with that in terms of your design and installation. And if you're not and you want to do things a little bit differently, hopefully this video has given you some ideas of the things you can try and incorporate into your design to cover those things off. Because the areas we're installing this equipment into really leaves us no option other than the approach that we've taken. So the pollution categories I've been discussing through the course of this video are well established in commercial and industrial environments, often a consideration that designers put in. It's perhaps not as widely known in domestic, and I say that as someone who didn't used to know about this stuff. Most of the things I've learnt along the passages of time are just from doing things. I've got all this stuff wrong before in the past. I've had selectivity where I've not even factored it into designs. Earlier on in my career, around fuses, MCBs, RCDs, all of that good stuff, I've not been perfect from the word go. I've picked stuff up from people around me, learned as I've developed as an electrician through the course of my career, and now I'm sat where I am now with a little bit more knowledge than what I started with, but still far from being an expert. So there's that journey we all go on, and pollution degree ratings is another one of those. So there's the 4 categories. One is basically like a test lab, so it's a clean room environment. You've not really got anything in there that's going to give you any issue to the electrical equipment you're using inside it. Pollution category 2 is typically kind of a domestic environment, indoors household environment. Pollution category 3 would be a commercial and industrial environments where you may encounter a degree of condensation and other aspects of corrosive polluting environments around the equipment in its use. Think of your typical warehousing and industrial units. You've all been inside them and seen them. And then pollution category 4 is equipment that's used outdoors. So realistically speaking, the equipment, if we're putting a consumer unit outdoors, should be pollution degree rated 4, in my opinion. Others may see it differently, but that's how I see it. And generally, if you look in the data sheets and technical specification on any of these consumer units that have been used outdoors, they're only rated to pollution category 2. So the equipment you're installing doesn't meet that. That's a grey area for people to deal with themselves. Obviously, you've got the UV resistance that the manufacturers are saying you've got on the metallic boards, most definitely. And then obviously the IP ratings as well. Point of note with that, if you're going to make big holes in the back of the enclosures, you're actually breaching that IP rating of the enclosure anyway. Same with top entry, you really need to make sure. We've all seen this on isolators that are used outside. If you go top entry, however well you seal those glands, you're always running the risk of having moisture enter into them. So at the very least, bottom entry would be my advice if you are going to go down that road. So these discussions are nothing that's new to industry. It's been raised in the past when forums used to exist, for those of you who are as old as me. And in more recent times, there was some chat maybe 3 or 4 years ago on social media, and a bit of a trend developed for spacing your MCBs and RCBOs to allow for heat dissipation and other magnetic effects that can occur around those when you've got them close together inside a consumer unit. There are some subtle and key differences, and we discussed this on the podcast back in the day, so the Electricians Monday Club. I think it was with Sam and Neil on that one, where we went into that kind of trend that had built up on social media, where we were seeing RCBOs with space in between every single one, and the misconception around that had developed, because there's a couple of key things that have to happen for it to be a factor in a consumer unit. One is that you're running your MCB RCBO towards its maximum rating, and another that you're doing it for a prolonged period of time. So really, it wasn't really a factor that occurred too often. If, for example, you've maybe got a hot tub next to an EV charger that's next to a heat pump, you could have an issue there, so it makes sense to space those apart or put some more lightly loaded circuits between them, just to try and reduce the ambient temperature and magnetic effects built up within the consumer unit. but it's rare. And if there is an issue with that, it's on the side of what I would call safety, where you have this nuisance tripping that might start to happen. There's no such thing as nuisance tripping. The devices operate for a reason, but essentially they're operating when there's no fault condition. It's just a circuit that's been used, but due to the derating that's needed inside the consumer unit, it's operating a little bit too quickly. When you get into colder unheated spaces and the pollution degree rating changes, that swings into what I would term the realms of danger, because they can allow more current to flow than you might be expecting because they're in a colder environment. So they're not operating too soon, they're operating too late, which for overload is more of an issue than perhaps a short circuit, for example, where you'd still hope to get the current flow you need to operate it. Now, obviously the maximum ZS values on that breakers can wander as well, which is why the derating is done to a large part. So if you have a design on your circuit that you're basing at 30 degrees ambient room temperature, but then you're installing your equipment in a location where it could drop to -15, you need to factor that in the maximum ZS values that you could be looking at as well, based on how the protective device is operating. So it's just understanding that. I think we all go on these learning journeys. I've been down these rabbit holes in the past. I've installed without regards to selectivity of MCBs, fuses, RCDs, have no awareness of pollution category ratings. I've been there and done all of those things. And you just pick stuff up through the course of your career. I'm maybe getting towards the realms of Dino Spark age range now at 42. So I'm not preaching this at anyone. I've made these mistakes in the past. I'm not perfect. Just talking about it to try and raise a bit of discussion out in industry among others and get some feedback myself. I learn and develop through sharing these videos and sharing content like this. So it is a bit of a learning exercise for me. I have a few things I'm not fully happy with on the install we've put together here on this video. I think there are a few tweaks that we need to make, and by sharing it I may get some awesome suggestions back, as I have had through Twitter actually just from sharing some pictures. So that's what it's all about. It's learning, building and developing together, which is fantastic. And just to put out there through sharing the reels on Instagram and stuff around all this over the course of the last week as well, I've had messages coming in where people maybe feel that the content I've been making is about them. I've had that feeling myself when I've seen content others produce before. It is an insecure world sometimes on social media, and our egos can get out of control when we feel like we're that important that other people would make content for us. Again, got that t-shirt. The reality is most people have better things to do with the time, as I most definitely do. This is just my views on a particular way of installing equipment. It's not aimed at anyone or anything in particular. There are absolutely loads of these EV installs going on every week where people are putting consumer units outside. It's not digging anybody out whatsoever. It's just my views on the regulations, pollution degree ratings, and our approach to try and engineer around it, if you like. So there's none of that going on whatsoever. I have been made aware of large WhatsApp groups that maybe exist discussing other people, and my name's perhaps popped into those. You know, that's part of a gossip club mentality. I want no part of that whatsoever. It's several levels of childishness below where I'm prepared to engage. But just to put it out there, if you are part of those places, it is just a toxic gossip club. I'd pull yourself out and do something better with your time, to be honest. And yeah, let's move on with this video. I'm not going to dwell on the negative aspect of all of that, but I did just want to cover it off. If you are sat there thinking that any of this is about you as an individual, then you are wrong. I'm so busy this end doing solar and trying to make videos like this that might be of help to other people that doesn't even register on my list of things to do. No disrespect to you sat there watching this.